Good morning to all. Today we will start a new module, rather than you can say a new chapter. The chapter is called Digital Filter Design. Okay, Digital Filter Design. Now, before starting the chapter, let me say you something about the filter and its use in digital signal processing. Okay, so why do we need a filter? Basically, in signal processing, a filter is used to remove unwanted parts of the signal, such as noise, or to extract useful parts of the signal, such as the components lying within a certain frequency range. Clear? Thus, a filter has two functions. What are those two functions? One is the separation of signals, and the other one is restoration of signals. Clear? One is separation of signals, and the other one is restoration of signals. Okay. Okay. Such filters may be of two types. This separation of signals and restoration of signals. These are done by two types of filters. What are those two types of filters? One is the analog filter, and one is the digital filter. So now, what is an analog filter? An analog filter uses circuits such as, rather than you can say circuit components such as resistors, capacitors, and operational amplifiers for filtering. Okay. On the other hand, a digital filter uses a digital processor such as a PC or a DSP chip to perform mathematical calculations on sampled values of the signal. In analog filter, the signal being filtered is an electrical voltage or current, which is the direct analog of the physical quantity involved. But in a digital filter, the signal is represented by a sequence of numbers rather than a voltage or current. Okay, you will not get any voltage or current such values. You'll get these only, but in the form of certain numbers, series of numbers. An analog to digital converter is used to convert the analog signal into digital form. The resulting binary numbers representing the successive sample values of the input signal are transferred to the signal processor. I'm just giving you a brief introduction, okay? So just listen carefully. If you want, you can note down also. This will be useful for you. It performs numerical calculations on these binary numbers to get the desired output. So what did I say? The resulting binary numbers representing sample values of the filtered signal are applied and transferred to the signal processor. It performs numerical calculations of these binary numbers to get the desired output. Now, if necessary, the result applied to a digital to analog converter, the sampled values of the filtered signal, to convert the signal back to the analog form. Okay, once I can convert it from analog to digital. Again, if necessary, I can convert from digital to analog. Such converters are also there. So digital filters are basically of two types. Okay, first, what is a filter? Then, what are the types of filters? Now, what are the types of digital filters? So, what are the types of digital filters? So, there are two types of digital filters: a recursive or infinite impulse response filter, and a non-recursive or finite impulse response filter. Okay. In the second type, the current output is calculated solely from the current and previous input values. But in the first type, that is a recursive filter, IIR, infinite impulse response filter, the previous output values are used in addition to input values. These previous output values are stored in the processor's memory in recursive filters. Digital filters form a very important part of digital signal processor. In fact, Their extraordinary performance is one of the key reasons that DSP has become so popular. Okay. Now, first we will discuss regarding the infinite impulse response filters. Basically, you see in your syllabus related to filters, you are just having the brief things related to infinite impulse response filters, related to finite impulse response filters. There are not much, so I'll be going as per your syllabus only. So please try to understand. It's very easy. Basically, the tough part of the subject we have already crossed up. We have already crossed the tough part of the subject. Z transform, discrete Fourier transform, fast Fourier transform. I'll be doing numericals also related to fast Fourier transform, related to the DIT and DIF algorithms. I have this in mind, but I thought of starting the filters today, so I have started it. Okay. So first we will deal with infinite impulse response filters. Clear? Okay. So before starting with infinite impulse response filters, let me share my screen so that all of you can view it. Okay, just a second. Okay, so now I think you are able to see. The heading is given digital filter design. Okay. Okay. So before looking into my notes, listen 2 lines. Then when I'll be saying you, then you will be observing the notes as and when I'll explain. Okay. So you see, basically a digital filter is a linear time invariant discrete time system. So I'm repeating again, a digital filter is a linear time invariant LTI discrete time system. The terms finite impulse response and infinite impulse response are used to distinguish the filter types. Okay. In digital filters, that means what does it mean? It means that in digital filters, why do we differentiate into 2 parts? The FIR, finite impulse response, and the IIR, infinite impulse response. Why? Because the digital filter, in general, a digital filter is a linear time invariant discrete time system. Clear? So the FIR filters are of non-recursive type. Now you look into the notes. The FIR filters are of non-recursive type, whereby the present output sample depends on the present input sample and previous input samples. The IIR filters are of recursive type, where the present output sample depends on present input, past input samples, and output samples. Clear? So now we will be dealing with IIR filters. Clear? You see, the impulse response HN, the impulse response HN for a realizable filter is, what is the impulse response in general for a realizable filter? It's HN equal to 0 for n not equal to or less than or equal to 0. Sorry, HN equal to 0 for n less than or equal to 0. Now, if we want this filter to be stable, so for stability, it must satisfy. For stability, it must satisfy summation of n equal to 0 to infinity mod of HN less than infinite. Clear? This is the condition that for stability, for a filter to be stable, what condition it should satisfy? This is the condition it should satisfy. Yeah. Now the IIR filters have transfer function of the form Hz equal to summation of n equal to 0 to infinity Hn z to the power minus, which is equal to, means you remember transfer function Hz transfer function, we have studied it in Z transform chapter. So equal to, if we describe it more in detail, then it will be equal to summation of k equal to 0 to capital N bk z to the power minus k divided by 1 plus summation of k equal to 1 to capital F a suffix k into z to the power minus k. Clear? This is the general expression. Okay. Now we have to design filter. So what do we do? क्या करना है? Design filter मतलब करना क्या? Design filter मतलब filter coefficients को निकालना. What are those filter coefficients? This a, k and b, k. A suffix k and b suffix k. So I've written, you see, the design is to find the filter coefficients ak and bk. यही हम लोग का काम है. ak and bk ये दोनों type of filter coefficients हम लोगों को निकालना है. Clear? Okay. Now let us come to the types of filter. So first let us know what is a filter again in short. You see, a filter is one which rejects unwanted frequencies from input and allow desired frequencies. Okay, filter means it rejects unwanted frequencies and it allows certain frequencies which are desired for us, which we desire, which we have marked out. So the range of frequencies of signal that are passed through the filter is called pass band, and those frequencies that are blocked is called stop band. Clear to you? The range of frequencies, again I tell you, the range of frequencies that are passed through the filter means that we allow are called pass band, and those we don't allow or those are blocked, those which are blocked by the filter is called stop band. Okay, so basically filters are of 4 types: low pass, high pass, band reject. All of you know it. So come to low pass filter. I'll be explaining it in very short. Low pass filter, you see, what is low pass filter basically? I've just drawn the graph, nothing else is written. So let me tell, listen to it carefully. If possible, you can note it down. Okay, if possible, note it down. It will be better for you. See, the magnitude response of an ideal low pass filter allows low frequencies in the pass band to pass, whereas the higher frequencies in the stop band are blocked. Clear? Low frequencies in the pass band are allowed, higher frequencies in the stop band are blocked. Now, you see, in the graph, I have marked a point mu ohm C. This ohm is nothing, it's the frequency. It is denoted like this. And suffix C means the cutoff frequency. Okay, so this is our cutoff frequency. This one is the cutoff frequency. So the cutoff frequency between the two bands, stop band and pass band, is the cutoff frequency. Now, what is its magnitude for low pass filter? Its magnitude is 1 by root 2. You see, first I have taken 1, then I have taken 0.707. Okay, so 0.707 means 1 by root 2. So in practical, basically, in practice, it is impossible to obtain the ideal response. All of you know it. But in general, for low pass filter, the cutoff frequency is 1 by root 2. Clear? And this is the graph. The dotted one is the ideal part, and the continuous line represents the practical curve. Okay? Okay. Magnitude response, basically. Now, this curve is what? This curve is nothing but the magnitude response of low pass filter. In fact, all curves are the magnitude response of that particular type of filter. Clear? Now come to high pass filter. It's just the reverse of low pass filter. You see, just the diagram is looking just like the reverse of a low pass filter. So the high pass filters allow high frequencies, means those frequencies which are greater than the cutoff frequency in the pass band, and those frequencies which are equal to or less than cutoff frequency are blocked, means these are falling under stop band category for high pass filter. Clear? Listen carefully. In high pass filter, frequencies greater than cutoff frequency comes under pass band. Frequencies equal to cutoff frequency or less than cutoff frequency comes under stop band. Okay. Similarly, magnitude response is shown here. Now come for band pass filter. You see, this is a band pass filter. There are two graphs. First one is the ideal. Actually, in low pass and high pass, you can show the ideal and practical curves in one within a pair of axes only. But for band pass and band reject, you need separate axis, XY axis, to show the ideal and practical curve. So the first curve is showing you the ideal one. The second curve is showing you the practical one. Clear? Now see, what is band pass filter? It means it allows only a band of frequencies. So you see there, pass band mu1 to mu2 means ohm1 to ohm2, means between ohm1 and ohm2 only those frequencies which fall, only those will be allowed in the pass band. The rest all the frequencies are in the stop band. It is not like that more than cutoff frequency, less than cutoff frequency. There is no such terms. A range of frequencies are given, a range is given. Within that range, the frequencies which fall will be in the pass band. Those which don't fall will be in the stop band. Clear? So it allows only a band of frequencies mu1 to mu2 to pass and stops all other frequencies. Okay. So ideal and practical curve you can see here. First curve is the ideal one. Second curve is the practical one. Okay. Now come to magnitude response, obviously. Okay. Don't forget, these all are curves of the magnitude responses, showing the magnitude response. Again, band stop or band reject filter. It's just the opposite of band pass filter, the diagram. So what is band reject filter? Band reject filter means within a particular range of frequency, it rejects those frequencies which fall, it rejects. Rest all the frequencies are passed. Means ohm1 to ohm2, if this is a range, then in between these range, the frequencies which fall comes under stop band. Rest less than ohm1, greater than ohm2, all comes under pass band. Clear to you? Just the opposite of band pass. So again, we have shown the ideal and practical curves of magnitude response for band stop filter. Okay. So now come to the difference between analog and digital filters. So what are the difference between analog and digital filters? You see, analog filters, they process analog inputs and generates analog outputs. In digital filters, they process and generate digital data. In the second point, they are made from active or passive electronic components. Here, they consist of elements like adder, multiplier, and delay. Third point, analog filters, they are described by differential equation. Remember, analog filters are described by differential equation, but digital filters are described by difference equation. I'll be telling you what is a difference equation. In the next lecture, you'll be seeing a difference equation for a typical digital filter. In the fourth point, the frequency response can be modified by changing the components for analog filter. If you change the components, you can change the frequency response, or you can modify the frequency response. But for digital filters, frequency response can be changed by changing the filter coefficients. Okay, frequency response can be changed by changing the filter coefficients. So apart from this, let me explain you. This is not written in my note. Afterwards, when I'll be giving the complete note, then there will be the advantages and disadvantages of digital filters. So today, let me tell you. If you want, you can write also. I'll be telling very slowly. Later on, when I'll be giving you the total note for filter design, then there will be present. But for the timing, if you want, you can write. You see, there are a lot of advantages and disadvantages for digital filters. Obviously, everything has its own advantage and disadvantage, isn't it? So, what are the advantages? See, number one, the performance of a digital filter is unaffected by factors like temperature, power supply variations, component aging. Component aging means, suppose a resistor, it's very old. So, will it work? Will it have its proper value till then? So, these are the things that you can say. So, this is one type of advantage. Second advantage, a digital filter has a high degree of immunity to noise and parameter stability. Third, digital filters do not have problems of input and output impedance matching. Fourth, digital filter provides the facility for multiple filtering. Fifth, digital filter can operate over a wide range of frequencies. Now, what are the disadvantages? Digital filters are costly, remember. And one more disadvantage, it's very important, is quantization error is present in digital filter. Why? Due to finite word length. There's a separate chapter basically. It's not present, finite word length. So you just know that the quantization error is present. Okay. So that's for today. Thank you.